So today we are going to discuss the stress path. Okay, so up till now we have been discussing how to do the triaxial test, right, and we apply the confining stresses, the cell pressure. We apply the cell pressure, and then we apply after application of cell pressure when we either in unconsolidated state or we can do the consolidated sample by allowing the drainage. All right, so after that we apply deviatoric stress to cause shear failure of the sample. So we have discussed various conditions. All right, so first of all we have discussed that there are two stages in triaxial test. So one is cell pressure application. One is cell pressure application. Then the other is the deviator stress application. Right. So in the cell pressure, we apply the pressure through the water in the cell, right? And the sample is in between, and the sample is in between. And then in the deviator stress application, we apply the load through the ram. Basically, we apply a displacement to the sample. We move the sample upward and we measure the reaction in the dial gauge. All right, we measure the reaction in the dial gauge. So as the sample moves up, the sample gets compressed, and the reaction, which is whatever the sample gives, that is measured in the dial gauge. And ultimately at a particular point when the soil fails, we see that the reaction becomes constant. So basically we can say that the load applied through the ram into the sample becomes constant. Just like in uh, direct shear test. So in direct shear test, what we do, we apply a normal force and then we move the bottom part. The bottom part is moved and we measure the, so when it moves in this direction, we measure the reaction from the sample using the dial gauge. So what happens is that proving ring, sorry, the proving ring. Okay, so the proving ring, what happens, it gives a reaction to the sample and the sample shears, and the reactive load of the sample, all right, the maximum tangential stress that the sample can take, we measure using the proving ring. Similarly here also we have the proving ring, and when the sample moves up, the proving ring applies the reaction onto the sample applies the reaction onto the proving ring. All right, and ultimately when the sample shears, we see that the reaction becomes constant, the force between the two becomes almost constant, and we see that sigma deviator becomes constant. So we have two stages, one is cell pressure, one is deviator stress application, and in both the two stages either we can keep the soil undrained stage, all right, or we can allow drainage. So when we apply drainage, there is no excess pore pressure generation. Right? Excess pore pressure generation. So delta U is equal to 0. So in that case, whatever load we apply, in case of drainage case, delta sigma, alright, is equal to delta sigma dash. So the incremental load, whatever we apply, the incremental stress, whatever we apply onto the sample, that is ultimately transferred to the effective stress within the sample. Whereas in the undrained case, what happens? There is no drainage. There is no drainage. There is no drainage. So there is no consolidation. Alright, and whatever load delta sigma, total load we apply, total stress we apply, ultimately that is transferred to the pore water pressure generation, obviously in the normally consolidated case. Now we need to assess the ways these stresses within the soil, it changes its state from one state to the other. All right, so if you see the if you see in our triaxial test also, we took out the sample, so we had zero total stress. Then we had some amount of residual pore water pressure, and then we started applying cell pressure. Right, we started applying cell pressure, and then there is development of effective stress and pore water pressure in the sample. Then we apply deviatoric stress. Then there is shearing in the sample. Then there is again some changes in the pore water pressure, or there may be drainage. All right, and ultimately the sample fails. All right, so ultimately, what are the difference? How the stresses they change from one condition to the other, and at what condition of stress, what configuration of stresses, the sigma C, sigma D, at what configuration U, all right, the soil ultimately fails. So we need to assess that. So to understand that, or to comprehend that particular aspect, we have developed what is called the stress path. So what is basically stress path is, so let us consider this sample, right? So what is the total stress in the sample? First of all, the total stress in the sample is equal to this bulk unit weight into H1. So gamma bulk into H1 plus, so this is saturated, so this is saturated unit weight, all right, plus gamma saturated into H2. So this is the total stress. Then what is the pore water pressure? All right, so pore water pressure is gamma W into H2. Gamma W into H2. Now if I draw that, all right, now here again, so this is sigma V. Right, so this is the vertical stress here. So this is the vertical stress here. And this is the horizontal stress, which is sigma H. So this is sigma V. So what is sigma H? So sigma H is equal to K naught into sigma V. Right? So let us now plot the stress condition in this particular sample. So first of all, let us plot the total stress. So we have sigma v here. All right, so we have sigma v here, and we have sigma h, which is k naught into sigma v. We have sigma h here. So basically, if I consider this sample, if I consider this element of soil, we have sigma v in the upper, in the horizontal surface, and we have sigma h in the vertical surface. So ultimately, we can say that actually it is subjected to some amount of shear also. So there are shear in the sample also. So we can draw the Mohr circle. So will the sample fail in this state? So we observe that the shear strength of the soil is given by this failure surface. So this is tau is equal to C plus sigma m dash tan of phi dash. Okay. Now obviously this is total stress. This is total stress. And this is shear stress, and this is normal stress. Right. Now what about the effective stress condition? So this is total stress. What about the effective stress condition? Obviously we know that pore water pressure, if it is u at a point, it is same in all direction, right? So it is same in horizontal direction as well as vertical direction. So we have sigma v dash is equal to gamma bulk H1 plus gamma saturated H2 minus gamma W H1 or H2, sorry. Okay, and sigma H dash is equal to K naught sigma V is equal to minus into H2. Right, so it is, if we see, this is the total stress. All right, so ultimately we can say K naught sigma V dash. All right. So here what will happen is that this total stress Mohr circle, if you see, this will be reduced by pore water pressure, this will be reduced by pore water pressure. So ultimately both these 2 points will shift in the negative, negative normal stress direction. All right, in this direction. So we have to subtract, we are subtracting the pore water pressure from both the condition. So we have this effective stress Mohr circle. All right, so this is the effective stress Mohr circle. Now suppose, so here we had the groundwater table here in between. All right, so at the depth of h1 from the surface. Now suppose the groundwater table moves up. All right, the groundwater table moves up. So it was initially here, so it moved up, all right, to the ground surface. So here what is the total stress again? So sigma phi is equal to, we have gamma saturated into H or Z. In this case it is written here, so it is Z, or that is sigma phi, and the pore water pressure is equal to gamma W into Z. So we have sigma V dash is equal to gamma saturated minus gamma W whole into Z. So again, if we plot here now, what will happen is that, so compared to this condition, so when the groundwater table will rise, what will happen is that the pore water pressure will rise. So say this effective stress Mohr circle will again move to the negative normal stress direction. All right, so that means it will now come here. So this is the rise in the pore water pressure due to the rise in the water table. And this was the initial case. So this is basically the stress path. So this is basically the stress path. So this is for the hydrostatic condition. This is for the hydrostatic condition. Right? And there is change in pore water pressure. Now suppose we have here, so this was the failure surface. All right, so tau is equal to C plus sigma n dash tan of phi dash. All right, so we had the total stress Mohr cycle here, right? And initially the groundwater table was here, suppose we considered. All right, so this is the groundwater table. So we had the Mohr cycle, effective stress Mohr cycle here. Now when the groundwater table will rise, what will happen? Now here you see, so initially we had gamma bulk into H1 plus gamma saturated into H2. So the total stress will also a little bit increase because now we have higher density at this range, at this state we have higher density. So the total stress will move slightly to the right, slightly to the right. All right, and then what happens? We have to subtract the pore water pressure, so effective stress will again move to the left. So this is the increase in the total stress due to the increase in the groundwater table, and this is the decrease in the effective stress due to the increase in the pore water pressure due to the rise in the groundwater table. So this is the stress path of this sample, of this element in the soil. So due to rise and if it falls, so if it falls, what will happen? So we had the total stress here, and if it falls, what will happen? So this gamma bulk now region will increase, so the total effective stress, total stress will slightly decrease than what was initially, so the total stress will slightly decrease. But what about the effective stress? All right, the effective stress will now increase. So initially it was here, so it will now maybe move on to here. So it will now move on to here. So there is an increase in the effective stress due to lowering of the groundwater table. So that is what is happening in this element. So that is the stress path due to change in pore water pressure due to rise and fall of groundwater table. Now here you see how tedious it is to plot it in terms of the Mohr column. The Mohr circle. All right, it is so difficult. So now, if suppose the groundwater table rises, all right, if it rises, so definitely. So if the effective stress was here and the total stress was here initially when the groundwater table was here, so after the rise, definitely, so the total stress will a little bit increase because this amount of weight of water is there now. All right, so that total stress will slightly increase, so it will go to the right. And whereas effective stress now, all right, so the effective stress, what will happen is it will significantly decrease. All right, so it will move to the left. So in case of earthquake also, so there is rise in groundwater table, rise in pore water pressure. So we can represent it as rise in groundwater table as well, but it is better not to represent it that way because it gives a wrong kind of impression, because that is due to the vibration in the soil element. Okay, and the soil element, the soil particles, they try to collapse into a denser state. All right, and whereas the water molecules, they vibrate in all directions, all right, and then they when there is a soil particle, the water molecules will try to push it up, all right. So ultimately there is a rise in pore water pressure. So due to that, what happens, the effective stress may ultimately reduce to 0. So here it will come up to this point. So the more circles will also reduce in diameter, and diameter, ultimately it will be, there will be no diameter. It will be sigma v is equal to 0, sigma h is equal to 0, and there will be, that is dash, okay, sigma v dash equal to 0, sigma h dash equal to 0, and there will be liquefaction. Right? So that is the stress path. So this is, of course, we have horizontal soil layer, right? If we apply a load on the surface, obviously there will be stresses generated in the soil, right? If we increase this load, then there will be increment in the shear stresses, okay. So here what will happen, the stresses will increase. So how the stresses increases, all right, how the stresses increases, all right, or decreases, and ultimately leading to a failed state or a yielding of the soil, that is the stress path, okay. So that is the stress path. So up till now we have been considering only the normal stress. So suppose we have here cell pressure we have applied. So we have applied cell pressure, right? So we have cell pressure, suppose 200 kPa, and we measure the pore water pressure at that point. So suppose we have 100 kPa. So now we have the point here 200 kPa, and the point here 100 kPa. Because say during cell pressure, you know, sigma 1 is equal to sigma 2 is equal to sigma 3, right? And similarly sigma 1 dash is equal to sigma 2 dash is equal to sigma 3 dash. This is shear stress and this is normal stress. Okay, now so there is pore water pressure, so that is what we have. So if we subtract this, so this is sigma dash, all right, and sigma c dash, okay, and say this sigma c total, all right. So this is cell pressure is 200 kPa, and effective stress in the soil, all right, pore water pressure is 100 kPa. So then we shear the sample. So as soon as we shear the sample, what will happen? So starting from the 200 kPa, so already there is 200 kPa of sigma 1 here, all right. So sigma 1 value is already 200 kPa, it is equal to sigma 3, all right. Now we apply sigma d. So whatever sigma d we apply, it will go on adding on to the sigma 1, all right, and sigma 1 will go on increasing. So that means the more coulomb, more circle will go on building. It will go on building. So sigma c is at 200 kPa. So sigma c is at 200 kPa. So sigma c is at 200 kPa. And then when we apply sigma d, so initially it is this amount, then this amount and this amount, ultimately it will go on adding, and this is sigma 1 and this is sigma 3 total, all right. So this is the total stress. So With application of deviatoric stress, there may be change of pore water pressure. If we if we I mean if I mean we I mean do the shearing in undrained condition. All right, we do the shearing in undrained condition. So we will come to that later. So let us assume that we have a pressure maintained here. We call it back pressure. We call it back pressure at 100 kPa. All right, and whatever increment of pore water pressure above that. All right, so if we shear the sample and suddenly the pore water pressure from 100 kPa goes up to 110 kPa, so there is drainage, and the pore water pressure is stabilized to 100 kPa. So the pore water pressure is maintained at 100 kPa. So that means the shearing is drained shearing. All right, at constant hydrostatic pore water pressure. So that is drained shearing. So whatever sigma d we apply, now same amount of increment in effective stress will also occur. All right, so we have the effective stress Mohr circles developing. All right, so the difference of these two is 100 kPa, which is the pore water pressure or the back pressure, which is maintained at 100 kPa. So this here we have represented the stress path with increment of Morse circle. All right, with increment of Morse circle. Now, so this is of course drained case. All right, so if we do the shearing in undrained case, then it is very difficult. It becomes very tedious case. So again we start at 200 kPa. So this is 200 kPa as in the previous case. This is 100 kPa of effective stress. All right, and the pore water pressure here U is equal to 100 kPa. Now we are not allowing any drainage and we are shearing the sample. Now obviously as we shear the sample, we are going to allow deviatoric stress to increase. So sigma d will increase, so along with the cell pressure, that will be sigma 1 here, and we have sigma 3, which is equal to the cell pressure. That is the total stress. All right, so that is the total stress. So as soon as we start increasing, we will have this initially Mohr circle. All right, so suppose this is 50 kPa, sigma d is showing 50 kPa, so this is 250. So that is sigma 1. Okay, sigma d is 50, sigma 1 is equal to sigma 3 plus sigma d, which is sigma 3 is 200 kPa. All right, plus sigma d is 50 kPa. So we have 250 kPa. So that is sigma 1. So this is 250. Then we increase. All right, so suppose 60, 70, all right, like that, sigma d is going on increasing, and similarly sigma 1 is also going increasing, and then since it will go on increasing, we will have incremental Mohr circle of this sort. Right. Now what about the effective stress? Now let us consider the soil to be normally consolidated. Let us consider the soil to be normally consolidated. So what will happen here is pore water pressure will be positive. So as soon as pore water pressure will be positive, what will happen? So the effective stress will reduce. So this point will also move in this direction. All right, will move in this direction, this point. So we have sigma 3 here, all right, and sigma 1 here. Then again with again increment of deviatoric stress, all right, there will be again pore water pressure increase. So again this point, which is suppose the delta U was 10 kPa, so we have the sigma dash now is equal to 100, which was initial minus 10. All right, so now we have 90 kPa. So sigma 3 dash has moved to 90 kPa. Then again we have, suppose delta U is equal to suppose 5 kPa. So now sigma 3 dash will be initially 90, so 90 minus 5 will be 95. All right, so this point will also move in this direction, and the Mohr circle will build up in this manner. And ultimately the soil will fail at this state. When this Mohr circle touches this failure surface, which is tau is equal to C dash plus sigma n dash 10 of phi dash, it will fail. So what is sigma n dash? So definitely we can find it out from this one. So if I plot stress paths in this way, if I go on plotting Mohr's circle for each increment of stress, then we are done doing stress path. So we cannot do that. All right. So if you remember, initially what we did, we used the MIT plot. Right? Initially the researchers, they used the MIT plot. So what they did was they told that okay, we will use S equal to sigma 1 plus sigma 3 by 2, and T is equal to sigma 1 minus sigma 3 by 2. So basically it is, if we plot it in terms of sigma and tau and the Mohr circle, so it is basically the center of the Mohr circle and the maximum shear stress value, right? So what if we plot it in terms of S and T, what will happen is that, so at a point sigma 1 is equal to sigma 3, all right, so and it is average of the two, so ultimately it is same, so it is equal to sigma 3, so we will have that same point, so 200 kPa here, and we will have 100 kPa here. All right, now if we plot it in terms of S and T, what will happen if as this Mohr circle here, as this Mohr circle goes on increasing, so we will plot these points. So you can see these points we can plot, which is actually T. If this is S, so we can join these points, and then we will have ST curve. All right, so from here the ST stress path will move in this direction. All right, so here what will happen is that we will have a lower slope than the total stress which is being applied. Right, so here the slope will not be as this one. All right, and ultimately there will be a point, all right, when it will reach there, when the ST plot will reach there, we have the failure. Right, we define the failure to be there, all right, or actually there will be constant deformation, with the stress being maintained. If we maintain the shear stress at that state, if we maintain the shear stress at that state, there will be flow in the constant flow, all right, constant flow in the soil, flow deformation in the soil. So it will keep on deforming, means it will keep on deforming. The shearing will continue at that state, all right, and there will be no change of pore water pressure, no change of volume, all right. So that is, we call it the critical void ratio state, all right, or a critical state of the soil. So this is the ST plot. Now this plot also had severe limitation, all right. So this plot also had severe limitation as far as the undrained condition is considered. If you consider the undrained condition like here, all right, so what will be the slope and how it will vary, all right. So this plot also had severe limitation, this ST plot, but still we can plot that, all right. We can plot that. In fact, we will plot the stress path also in terms of ST plot, and we will verify and compare, all right. We will compare the various plots. We will compare the various plots. Now, all right, so then it was seen that if we plot it in terms of the stress invariance, all right, if the plotting is done in terms of the stress invariance, then it is very advantageous, all right. So what was done after that was the Cambridge plot was developed. Okay, so the Cambridge plot was developed. So here what we have is, we have the P, which is the confining or the mean stress, all right. P is the mean stress. So P is equal to sigma 1 plus sigma 2 plus sigma 3 by 2, and P dash is equal to P minus U, and we have the deviator stress, or deviatoric stress, or the shear stress, or the distortional stress, whatever you say. So we have Q, which is equal to 1 by root 2 1 minus sigma 1 minus sigma 3 whole square plus sigma 2 sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, and then sigma 3 minus sigma 1 whole square, right? And ultimately, for axisymmetric condition in case of triaxial test, for axisymmetric condition in triaxial test, we have P is equal to sigma 1 plus twice of sigma 3 by 3, and Q is equal to sigma 1 minus sigma 3. Okay. Now, again we plot it in terms of this, plotted. So if we plot it, what will happen again? So now instead of sigma and tau, so we cancel this. Instead of S and T, we cancel this. Now we will plot it in terms of P and Q. All right. So P, when I say, it will be P comma P dash. All right. So mean stresses, whether it be total stress or effective stress, will be plotted in the x-axis, and the Q, which is the deviatoric stress, will be plotted in the y-axis. Obviously Q is independent of the pore water pressure. Alright, so pore water pressure has no effect on Q. So when we go on increasing cell pressure, what will happen? The effective confinement will go on increasing, because it is increasing in all directions. It is increasing in all directions, so the effective confinement will go on increasing. So we have, so suppose we consider this sample. We took out the sample, and now it is 0, sigma V is equal to 0, and similarly sigma H is equal to 0. And we have some amount of pore water pressure, but we will consider it to be equal to 0. So ultimately all of the stresses are here at this state. Alright, we assume that because there is no way of measuring this pore water, so we assume that the pore water pressure initially at the sample is also 0. Then we start to increase the cell pressure, so the total mean stress, alright, total mean stress P is equal to sigma 1 plus twice of sigma 3 by 3, so it is equal to sigma 1 is equal to sigma 3 in cell pressure increment stage. In the cell pressure increment stage, sigma 1, here whatever water pressure is applied, same is here applied here. Alright, sigma D is equal to 0, so that is increment, cell pressure increment. So here sigma 1 is equal to sigma 3. Ultimately we have P equal to sigma 3. So we go on increasing the cell pressure, or we can say sigma C. So we go on increasing the cell pressure, and this point the total stress, mean stress, will move in this direction. Alright, when we apply the cell pressure. So suppose we are here at the point. So this is suppose 150 kPa. So the pore pressure will also increase. The pore pressure is suppose 75 kPa. We are measuring here. U is equal to 75 kPa. So we have the 75 kPa here. Then what we did, we increased the cell pressure to suppose 200 kPa. Alright, and we observe that the pore water pressure is now U is equal to 100 kPa, it is showing. So there is increment in the effective stress as well as increment in the total stress. So now we have the point here, this is 200 kPa. So the point will move from here, this is the total stress point, to here, which is 200 kPa. Which is 200 kPa. Similarly, this effective stress point will also move to 100 kPa. Now suppose we increase the cell pressure to 300 kPa. Right? And definitely the pore water pressure will also move to 200 kPa. So this difference will now hold. Right? And if we go on increasing the cell pressure in undrained condition, the effective stress as well as the total stress will go on increasing in this manner. Alright, because only the confinement, the total effective and the total confinement is cell pressure is increasing. There is no deviatory stress. If we allow drainage, so now suppose we are at the cell pressure stage of 250 kPa and we see that the pore water pressure is also showing 150 kPa. So we start at that point. So we have 250 kPa here. So this is 250 kPa. And we have the effective stress here, which is showing 150 kPa. Right, so this is the effective confinement P dash, and this is the total confinement P. Okay. This is P. Then, if we now allow drainage, what will happen? Pore pressure will reduce. So if I allow the drainage, and suppose I maintain a back pressure of, so here what I do, I maintain a back pressure of suppose 50 kPa, right? So ultimately what will happen? So pore pressure was here initially 150 kPa, so definitely there will be drainage out of the sample, alright, and ultimately the pore water pressure will also show, the pore water pressure will also show 50 kPa. So that means now the pore water pressure inside the sample is reduced to 50 kPa. So this point will remain here as it is because the cell pressure is to 250 kPa. So, and this point what it will be, so this point will shift, sorry, this point will shift to the right now, right? The effective stress will increase. All right, so what is the effective stress now? So effective stress is 250 minus pore water pressure, so this is cell pressure minus pore water pressure, so this is pore water pressure, so it is P dash is equal to 200 kPa. So it will move from 150 to 200 kPa. Okay. Now suppose what we do, so we have this point, suppose here this is 200 kPa. Okay, so this is 200 kPa of effective stress after the consolidation. So now this, if now what we do, we apply the deviatoric stress. Okay, it got deleted anyway. So now we apply the deviatoric stress. So we have this condition achieved. All right, so we have P here 250 kPa, that is the cell pressure. All right, so that is the cell pressure. We have here 250 kPa, and we have here 200 kPa, which is the effective confinement. All right, so P dash is equal to P minus U. U is 50 kPa, which is showing here. U is equal to 50 kPa showing. And here also we are applying a back pressure, which is equal to the hydrostatic pore water pressure. So it is equivalent to the hydrostatic pore water pressure. Right? So that is also showing 50 kPa. So this is the effective stress condition. So we are here. Now if we allow drainage, right, while maintaining this 50 kPa hydrostatic pressure, so when we start applying sigma D, so the soil will shear, right? There will be shearing started in the soil. So what will happen is, now Q, so sigma 1 will start increasing, right? The increment will be equal to the sigma del sigma D, whatever increment we give, right? So sigma Q is equal to sigma 1 minus sigma 3. So sigma 1 will start increasing, so Q will now start increasing, right? And if we allow drainage, so there will be no pore water pressure, delta U is equal to 0. So whatever difference is, it will remain the same. That is, this hydrostatic pore water pressure will maintain at this. So if the pore water pressure develops more than, slightly more than 50, so suppose it is 50 now, so we apply shear. We apply, suppose sigma D is equal to 10 kPa, as we have discussed earlier. So the pore water pressure develops to 50 2 or 3 kPa. So that 3 kPa bore water pressure, whatever suddenly in a momentous, I mean in a small amount of time, infinitesimal amount of time, whatever it will develop, it will dissipate and it will drop down to 50. So basically we will consider that excess pore water pressure generation will be zero. Alright, so there is drainage and therefore there will be no excess pore water pressure generation. Only this will remain. So here, as I go on applying sigma D, so there will be increment in Q, and this point now will move in this direction, like this. Alright, or if you remember, P is equal to sigma 1 plus twice of sigma 3 by 3. So with increase in sigma 1, P will also increase, and with increase in sigma 1 now Q will also increase. Q will also increase. So the Q value will start increasing. And if we do the drained shearing, if we do the drained shearing, then this effective stress path will also be in the same direction as the total stress path. Right? And this difference will be the hydrostatic pore water pressure, which is the back pressure. Okay, so that will be U will be equal to the back pressure. Now this slope, right, this slope is 1:3 always, right? So it is up to you to find it out why it is 1:3 always, because it is because of the way we represent Q and P. Alright, so this slope is always 1:3, and this is the drained stress path. Okay, now if it is undrained, if it is undrained, so in that case, and if it is normally consolidated, alright, so there will be development of pore water pressure. So there will be development of pore water pressure, delta U will be generated. So what will happen as soon as delta U or pore water pressure will be developed, so we start from 50 kPa, that is we start from 50 kPa. So we, as we increase the sigma D, the pore water pressure will go on increasing. So it will from 50 it will go to 51, 52, 53 as we go on shearing. Alright, it will be increasing. Similarly, sigma D will also be increasing, so Q will also be increasing. Alright, and P, what about P now? So P dash, effective confinement, is equal to P minus U. Now P is remaining constant, so it is at 250. Alright, it is at 250, or it is at 200. P dash is at 200 and P is at 250. So what will happen? So from here onwards, right, initially the stress path will remain straight for a small amount, for a small value. Alright, for a small value of deviatoric stress, it will remain straight. This is called the elastic region of the soil sample. Then from there onwards, it will go in this direction, and then in this direction, and then it will stop somewhere. Alright, so this is the failure point. Okay, in that case, for this sample, it will be the same, this one, so it will fail somewhere on top here. Alright, so now we will see why this particular curve is there. in the next class. Okay, I think for today this amount of stress path is enough. Right, so you kindly just follow through whatever I've discussed. Okay, so we will stop here today.